Both mesh and nodal analysis are systematic ways to apply Kirchhoff's laws to linear circuits. The key assumptions are: all elements are linear and time invariant. The circuit is in steady state, with no energy storage effects unless represented by equivalent impedances. The network is planar for mesh analysis, with no crossing branches. A mesh is a loop that does not contain any other loops inside it, like a closed sidewalk around a park. A node is a point where two or more circuit elements meet, similar to a traffic intersection. The analysis treats the whole circuit as a water pipe system. Currents are the flow of water, voltages are pressure differences. By choosing either mesh currents, one unknown per independent loop, or node voltages, one unknown per essential node, we reduce the problem to solving a set of linear equations. In mesh analysis, we assume each mesh carries a constant current, the mesh current, that flows clockwise or any chosen direction. The actual branch current is then the algebraic sum of the mesh currents that pass through that branch. In nodal analysis, we assume each node has an unknown voltage relative to a reference node, ground. The actual branch current is given by Ohm's law using the voltage difference between the two nodes it connects. These two viewpoints are interchangeable, and the choice depends on which gives fewer equations. Explanation: to derive mesh equations, start with Kirchhoff's voltage law, which states that the sum of voltage drops around any closed loop equals 0. Consider a simple circuit with a 10-volt source Vs in series with a 2-ohm resistor R1, and a parallel branch containing a 4-ohm resistor R2 and a 1-ampere current source Is oriented upward. Identify two meshes. Mesh 1 encloses Vs R1 and the top branch. Mesh 2 encloses R2 and the current source. Assign clockwise mesh currents I1 and I2. Write Kirchhoff's voltage law for each mesh. Mesh 1, negative Vs plus 2I1 plus 4I1 minus I2 equals 0, which simplifies to 2I1 plus 4I1 minus I2 equals Vs. Mesh 2, 4I2 minus I1 minus 1 ampere times Rec equals 0, which simplifies to 4I2 minus I1 equals 0, because the current source forces I2 minus I1 equals 1 ampere. Because the current source lies on the shared branch, we replace the Kirchhoff's voltage law equation for mesh 2 with the constraint I2 minus I1 equals 1 ampere, which is a super mesh situation addressed later. Solving the two equations gives the mesh currents, from which any branch current or voltage can be found. The derivation illustrates how each term in Kirchhoff's voltage law corresponds to a physical drop. Resistor voltage equals resistance times the current through that resistor. Explanation: nodal analysis starts from Kirchhoff's current law, KCL. The algebraic sum of currents leaving or entering a node equals 0. Take a sample circuit. A 12-volt voltage source Vs connected to node A, a 3-ohm resistor R1 from node A to node B, a 6-ohm resistor R2 from node B to ground, and a 2-ampere current source entering node B from the left. Choose ground at the bottom of R2. Let VA and VB be the node voltages relative to ground. Write KCL at each non-ground node using Ohm's law. I equals voltage difference divided by resistance. Node A, voltage A minus 12 divided by source resistance, if the source has internal resistance, plus voltage A minus voltage B divided by 3 equals 0. This becomes voltage A minus 12 divided by infinity plus voltage A minus voltage B divided by 3 equals 0, which simplifies to voltage A minus voltage B divided by 3 equals 0. Therefore, voltage A equals voltage B. If the source is an ideal voltage source, it forces voltage A to be 12 volts. Node B, voltage B minus voltage A divided by 3 plus voltage B divided by 6 minus 2 amperes equals 0, which simplifies to voltage B minus voltage A divided by 3 plus voltage B divided by 6 equals 2. Solve the second equation, multiply by 6, giving 2 times voltage B minus 12 plus voltage B equals 12. This simplifies to 3 times voltage B equals 36, so voltage B equals 12 volts. Thus voltage A equals 12 volts as well. The node voltage method gave us the same result with only one equation because the voltage source directly set a node voltage. Each term in the KCL equation corresponds to a river flowing into or out of a junction. The sum must balance. After writing mesh current or node voltage equations, we obtain a set of linear equations of the form AX equals B. where A is a square matrix of coefficients, X is the vector of unknown currents or voltages, and B contains independent source terms. Determinants. For a 2x2 system, the determinant a bar equals a 11 times a 22 minus a 12 times a 21 tells whether a unique solution exists, a bar not equal to 0. For larger systems, the determinant can be expanded by cofactor or row reduction, but hand-calculating determinants beyond 3x3 becomes cumbersome. Kramer's rule provides closed-form expressions. xi equals the determinant of ai divided by the determinant of A, where a I is the matrix A with column I replaced by B. Example for a 3-mesh circuit. The coefficient matrix is 4, -1, 0, -1, 5, -2, 0, -2, 3. The current vector is I1, I2, I3. The right-hand side vector is 10, 0, 5. Compute the determinant of A. 4 times the quantity 5 times 3 minus -2 times -2 minus -1 times the quantity -1 times 3 minus 0 times -2. This equals 4 times the quantity 15 minus 4, minus -1 times -3, which simplifies to 4 times 11 plus 3, giving 47. Then replace column 1 with B to get the determinant of 1, and so on, yielding I1 equals determinant of 1 divided by 47, and similarly for the other currents. Computational tools. In practice, engineers use matrix solvers in MATLAB, x equals a \b, Python's NumPy, x equals np-lnog solve of a comma b, or circuit simulators, SPICE. These perform Gaussian elimination or LU decomposition automatically, handling large systems 10 to the 4th unknowns efficiently. The key is to assemble it correctly. Each row must correspond to one KVL or KCL equation and each column to one unknown. Real circuits often contain dependent controlled sources, which make the equations slightly more involved. A voltage-controlled voltage source VCVS, or current-controlled current source CCCS, introduces terms that are proportional to another current or voltage in the circuit. When writing mesh equations, replace the dependent source voltage with its controlling variable, for example Vx equals K times Ix. In nodal analysis, replace the dependent current with K times Vx, where Vx is the voltage at the controlling node. Supermesh. If a current source lies on a branch shared by 2 meshes, KVL cannot be written for those meshes individually because the voltage across an ideal current source is unknown. Instead, encircle both meshes together, forming a supermesh that excludes the current source branch. Write KVL around the supermesh, and add a constraint equation relating the 2 mesh currents to the known current source value I1 minus I2 equals Is. Supernode. Analogously, when a voltage source connects 2 non-reference nodes, KVL or KCL cannot be applied directly at each node because the node voltages are linked by the source voltage. Create a supernode that includes both nodes and write a KCL equation for the combined node. Then add a constraint V node 1 minus V node 2 equals Vs. Dependent voltage sources are handled the same way, with the constraint expressed in terms of the controlling variable. Source transformation is a powerful technique that lets you replace a voltage source in series with a resistor by an equivalent current source in parallel with the same resistor and vice versa. I equals V over R. This is useful when a source blocks the direct application of KVL or KCL. For example, in mesh analysis, a voltage source inside a mesh can be troublesome. Converting it to a current source may eliminate the need for a supermesh. Conversely, in nodal analysis, a current source that is in parallel with a resistor can be turned into a voltage source, simplifying the KCL equation at that node. The Venin-Norton equivalents compact a whole network scene from a pair of terminals into a single voltage source VTH in series with a resistance RTH, or a current source IN in parallel with a resistance RN. When solving a large circuit, you can replace a complicated subcircuit that connects to the rest of the network by its Thevenin or Norton equivalent, reducing the number of unknowns. For instance, in a mesh problem, you might replace a set of resistors and independent sources attached to a branch by its Thevenin voltage and resistance, then treat that branch as a simple series element in the mesh equations. The transformation steps are: open circuit the terminals to find VTH or short circuit to find IN. Turn off all independent sources, set voltage sources to 0 volts, short current sources to 0 amperes, open to find the equivalent resistance RTH. Use I equals V over R to switch between the Thevenin and Norton as needed. These equivalents preserve the external IV relationship, so any mesh or nodal solution will be unchanged. Both methods are systematic, but each has strengths. Mesh analysis. Best for planar circuits with few loops and many nodes. Number of equations equals number of independent meshes L minus N plus 1, where L is number of loops and N is number of nodes. Handle series connected elements naturally. Difficult when many current sources lie between meshes, requires supermeshes, or when the circuit is non-planar. Nodal analysis. Best for circuits with many nodes and few loops, especially when many voltage sources are present. Number of equations equals number of essential nodes minus 1 ground. Handles parallel connected elements naturally. Requires supernodes for voltage sources between non-reference nodes and special care for dependent sources. Selection criteria. 1. Count unknowns. Choose the method that yields the smaller set of equations. 2. Look at source types. Predominant voltage sources leads to nodal, predominant current sources leads to mesh. 3. Geometry. Non-planar circuits, for example with crossing wires, are easier with nodal analysis because mesh analysis may need extra equations for each cut. 4. Computational convenience. In simulation tools, nodal analysis is the default because it leads to sparse matrices that are efficiently solved. In practice, engineers often switch between the two during a single problem, using source transformation to turn a troublesome current source into a voltage source, for example. Problem 1. Simple mesh. Circuit, 15-volt source in series with 5 ohms, shared branch with 10 ohms resistor, and 2 amp current source between the two meshes. Steps. Step 1. Identify two meshes, assign clockwise currents I1, I2. Step 2. Write KVL for mesh 1, excluding the current source. 15 minus 5 I1 minus 10 times I1 minus I2 equals 0. Step 3. Because the current source lies on the common branch, write constraint. I2 minus I1 equals 2 amps. Step 4. Solve the two equations, resulting in I1 equals 1 amp, I2 equals 3 amps. Step 5. Find resistor voltages. V5 ohms equals 5 times I1 equals 5 volts. V10 ohms equals 10 times I1 minus I2 equals negative 20 volts, drop opposite to assumed direction. Problem 2. Nodal with dependent source. Circuit, node A connected to 12-volt source, grounded at the negative terminal, 4 ohms resistor to node B, and a V-controlled current source of value 0.5 times V sub AB flowing from B to ground. Steps. Step 1. Choose ground at the bottom of the dependent source. Step 2. Let VA equal 12 volts set by the ideal source, unknown VB. Step 3. Write KCL at node B. VB minus VA divided by 4 plus 0.5 times VA minus VB equals 0. Step 4. Substitute VA equals 12 volts, giving VB minus 12 divided by 4 plus 2 times 12 minus VB equals 0, which simplifies to VB minus 12 plus 24 minus 2 VB equals 0. Then negative VB plus 12 equals 0, so VB equals 12 volts. Step 5. The dependent source forced the same voltage at B. The branch current is 0 amps. Problem 3. Using the Thevenin to simplify a mesh problem. Circuit, a complex network of 3 resistors, 2 ohms, 3 ohms, 5 ohms, and a 10-volt source connected to a load resistor RL equals 4 ohms. Goal, find current through RL. Steps. Step 1. Remove RL and find the Thevenin equivalent at its terminals. Step 2. Open circuit voltage VTH equals voltage across the open terminals. 10 volts times 5 divided by the sum of 2 plus 3 plus 5, which equals 5 volts by voltage division. Step 3. Turn off the 10-volt source, replace with short, and find RTH as the parallel of 2 ohms and 3 ohms plus series 5 ohms, which equals 2 times 3 divided by 2 plus 3 plus 5, that is 6/5 plus 5, which equals 6.2 ohms. Step 4. Replace the network by VTH equals 5 volts in series with RTH equals 6.2 ohms, then attach RL equals 4 ohms. Step 5. Mesh current I equals VTH divided by RTH plus RL. 5 divided by 6.2 plus 4, approximately 0.45 amps. Step 6, voltage across RL equals I times RL, approximately 1.8 volts.